Oh, it's like a solid set. Oh, hi.
Okay. I think we can start.
Yeah. Is that for the Zoom? Is that for the people on this?
I mean, just usually recording. We want to make a video, record as a video.
A video? I look okay.
It's okay.
I can put on makeup.
It's my very great pleasure to introduce today's colloquium speaker, Professor Anand Pillay from the University of Notre Dame. Anand got his PhD in 1978 under Wilfred Hodges at Bedford College, London. And as of a couple of hours ago, he has 239 publications on MathSciNet with 3,299 citations, but that will probably change soon. He has a strong connection to the logic model theory group in this department. He was Ivo Herzog's PhD advisor. He's done papers with Gabe Conant and Carolyn Terry, and he was one of the early founders of the subject of omenality, which is certainly what I made my bones on in this business. It's really no exaggeration, I think, to say that every model theorist of my generation, and possibly his as well, has been affected by his work. So I'm very happy to have him here speaking. As you say, the title is Approximate Subgroups and Topological Dynamics.
Thank you, Chris. Okay, thanks for the invitation, for the introduction, and it's nice to be here and to see you. It's the first time I've been. I spent a lot of my life in the Midwest, on the United States of America, as opposed to somewhere else. And I never came before to Columbus or visit here. So good. So I'm talking about this topic, approximate subgroups, topological dynamics, and I don't know, it's something which a lot of people here may know more than I do about the subject. I think Charlie Bergelson, who couldn't be here, is not working around this. It's something about large sets and groups. Okay, that's what it's roughly about. And so then we start getting some. This doesn't work already.
Point to the computer.
Got a point where?
We need to focus on the video.
Okay, that's it's not like. What happened?
But it works before, right?
Yeah,
Can you check again?
Yes, good, thank you. Good. So let's just I start giving definitions. If that's a second. Yeah, I see you definitions. So I like definitions. So you take an arbitrary group, an X an arbitrary subset of G, and we'll call X an approximate subgroup if X is symmetric, which means X equals X to the minus 1. And finitely many left translates of X cover X times X, where X times X is just a collection of XY. A collection of well, you can use it for X times Y, lots of okay. This is a definition. And we call right, sometimes you want to bound the number of so left translates, I think you know what I mean, multiply on the left by 11, and how many of these, so finally many, you may want to bound the number of translates, you say K approximate. Example, minus 1, 1 is a 2 approximate subgroup of R plus. Because if you take minus 1, 1 times it, okay, minus 1, 1, so we're plus, right? You get minus 2, 2, and you're covered by, is that all right? 2 translate? You covered by that? Is that right? Anyway, okay. Yes. Okay. Fix D and natural number n, and you take, and now you work in D dimensions, and you look at this R1x1 plus R2 RDXT, so R1x1 plus RDXD, where R are real numbers of length of norm at most n. So this, I think they call it generalized arithmetic progression, kind of functions. Is a 2D approximate subgroup of D space over the roots. Another example, you take any locally compact group, and so this is the first two examples are a special quantified case of the third example. Take any locally compact group, and you take a relatively compact symmetric neighborhood. Symmetric means what I said before of identity. Then X is an approximate subgroup of G, because if you look at X times X, look at closure of X is compact. In X times X is an open subset of closure. The X is an open subset of, X would be an open subset of well, this is the closure, and this is compact. All right, so open compact, finitely many translates cover. Okay, so topology is the picture. And a special, sorry about this, a special case of this is when G is itself compact, and G is compact, and simply X is a symmetric neighborhood of identity, open neighborhood of identity. Then again, just because G is compact, finally translates as X cover G. So the point here is that you explain somehow approximateness, or approximativity, something. You explain it by topology. But we're talking about arbitrary groups here. Remarks. Now, I don't know, I've got about 12 slides. We have an hour. I'm not sure, I'm not timing things correctly, so I may finish very early, I may finish very late. I'm just not, I didn't compute things too well. I'm just going to start talking and okay, see how it goes. And please feel free to ask questions. A few remarks. So I think this notion was introduced by Tao in connection with generalized additive combinatorics. So generalized means going beyond a commutative situation, where usually X is finite. And in the finite case, for different reasons, you have to quantify the degree of approximativity. Okay? Otherwise, it doesn't make sense. Because always a finite set will cover X times X just by being finite. For G commutative, these finite approximate subgroups were studied described in terms of generalized arithmetic progressions by Freeman, Russia, Green, if I'm not mistaken. I mean, Gabe and Caroline know a lot of the literature here, so correct me if I make an error. Now, okay. Actually, I'm going to say for arbitrary G, for arbitrary G, not necessarily commutative, and for finite approximate subgroups, they were also described in terms of what generalized nil progressions by Briard, Green, Tao, following work of Rashofsky, which had a model theoretic component. And so nilpotent groups enter the. So for arbitrary G, you explain somehow finite approximate subgroups in terms of nilpotency for different technical reasons. Now, the general theme or problem is to describe or explain approximate subgroups up to commensurability in terms of topology, which means the topological examples on the previous page. Locally compact groups, compact groups. So you start with just abstract group, abstract subset, totally combinatorial or discrete information, and you say, okay, this comes from topology. This is the theme of the whole business. Where you say X and Y are commensurable, X and Y subsets of a group are commensurable if finitely many translates of each cover the other. Okay. Okay, and again, one would like, in certain cases, even any time, to put bounds, even absolute bounds, on the number of translates involved in commensurability. So I'd give us kind of statement. So X with X, you've got X approximate, then X commensurable with Y via a certain number M, such that Y can be described in a certain way. And you want to say, well, we could bound M, maybe M depends on the choice of G, or maybe M depends on nothing. So it's like 5 or something, you know, it's not, I would call it an absolute number, like 57, right? Absolute number, or number, I suppose. Good. Some more remarks. Now this is important. There's also relative, so my context here is an arbitrary G and an arbitrary X. So this is just mathematics. There's a certain relative context where the data, G and X, are definable objects in a certain structure M in the sense of model theory. Now I don't want to give a model theory talk, so I don't want to talk about this relative context, but this is the, so the model theory context is somehow you're like in a certain situation where you're interested in a certain category of sets. It could be algebraic subvarieties, it could be semi-algebraic sets, it could be differential sets. You know, you're interested in a certain category, not all things. And this is an interesting thing, and the relative results are stronger results because they specialize to the case when everybody is definable, whatever that means. So in this talk, I'm positioning myself in the absolute context where if you're a logician, you work in the universe of set theory, which Harvey Friedman would like very much, but he's not here. Yeah, but G is a group, but everyone's definable. But forget about this. I'm working in a context where there's no restriction on the sets I'm talking about. But you could restrict and you get interesting theories and stronger theories. But I'll suppress this relative context. But this relative model theory context is very relevant to describing finite K-approximate subgroups, where you describe finite K-approximate subgroups in this, what Roshovsky was doing in his influence, we are calling tau, is you want to, you fix K, you look at all groups and finite K-approximate subgroups, and you take what's called a logical limit. In this logical limit, the finite thing becomes what we call a pseudo-finite, a non-standard finite object in a non-standard model of set theory. And you're in a relative context because you only consider certain sets which we call internal. But I'm going to suppress that. So I already said too much about that because I wanted to not talk about it, but I talked about things I didn't want to talk about. Okay, that happens sometimes. But you're free to ask about that ambient environment if you want. I mean, a lot of these, we were talking with Gabe earlier, a lot of these, some of the theorems are very close to things by Bergelsen and various people in the absolute context, but in the definable context, they're not. So that's why the definable context isn't true. But I'm not going to talk about that. Now, a stronger condition on X is that it's symmetric and is already commensurable with the full group G. Okay? Which means that it's symmetric and finally translates cover the full group G. So it's already commensurable with G. And I'm going to call this a generic approximate subgroup. So generic for, in certain contexts, the idea of a subset of a group for which finally it translates cover the group is called synthetic. I think in topological dynamics they use the expression synthetic. So it's synthetic approximate. Now in this situation, up to commensurability, X is just G. Right? So if you're interested up to commensurability, it's a vacuous problem because X is a group. Right? So endo, finish the discussion. So in this situation, which I'm going to focus on later, to have non-trivial statements, you'd require absolute bounds or relative bounds on the commensurability degree to say something interesting in this context of generic approximate rather than approximate. Okay. So I'm going to focus on this case later because the dynamics is something more easily accessible. So a more precise version of the goal, general, is to find locally compact models of an approximate subgroup. What's a locally compact model? The word model here has got no connection with model theory. The word model is used in the same way. I think it's Tau's expression for Lie model in finite approximate subgroups. Isn't it Lie model? He calls it. Tau calls Lie model. So it's nothing to do with it. It's a model in some senses like in.
But it was motivated by like the Freinen model in one that's.
Oh, it comes
Freinen-Ruger model.
It comes from a Freinen-Ruger model. There's some sort of anyways, no connection model theory, but called a locally compact model. What's the meaning? So I'll give a definition. By a locally compact model of an approximate subgroup, we mean a homomorphism from this X is the group the subgroup generated by X, which in general could be in infinitely many steps. A homomorphism from F from the subgroup generated by X to a locally compact group C, such that up to commensurability, X contains, and I want a homomorphism with dense image. I guess I want it with dense image. Is that right? I think such that up to commensurable, after replacing X by something commensurable with it inside the group generated by X, it contains the pre-image of a relatively compact neighborhood identity in the locally compact. Right? So when I say, so suppose X itself contains the pre-image of a relatively compact neighborhood identity in C, maybe symmetric, then if it does, whatever X is, X will have to be an approximate subgroup. Just by the example I gave before, right? By this example 0.3, right? Okay, I'm just saying this gives a topological explanation in terms of locally compact groups. Okay, and so that would be a locally compact model. It means up to commensurability, you can X comes from a relatively compact open set neighborhood identity in a locally compact group under some homomorphism. Okay. Now for X an approximate subgroup of G, I will say that the group, this angle brackets X is V amenable. This V is for this symbol here is a V. I'm not going to say where it comes from. Actually, it comes from logical symbol OR, but I don't want to talk about that too much. Okay? It's V amenable. If there's it's a version of amenability for groups which are generated by a certain set in infinitely many steps. This again is just abstract mathematics. There's no logic involved. We'll say this group is V amenable if there's a left invariant finally additive measure with values in the positive reals together with infinity on the collection of all subsets of the group generated by X, which gives, I should say something which gives U of xm is positive error, typographical error. I should say that the measure of X to the M, this is just the M-fold product of X, is positive and not infinity for all M. All right? So this is an analog of amenability of a group, of an abstract discrete group, but for when you look at the group generated by certain sets of imaginary. Okay? Now, I think of Masako-Wagner, we talked about this, Masako-Wagner, in my level of generality, this actually is probably, I said building on work of Wachowski, discussions with Gabe in the recent, today afternoon, actually, in my level of generality, which is very specific to just abstract mathematics rather than definability, it's actually contained in Wachowski's work, right? Well, I didn't say what the theorem is, so we have to. Suppose X is an approximate subgroup of G, and you have the assumption that the group generated by X is V amenable. Then there's a locally compact model for X where this M equals 4, which means that after going to X, if Y is this, so there's this map homomorphism, I think, with I want dense image from X to C, locally compact, such that F to the minus 1U is contained in Y for some nice U, and U being a relatively compact open neighbourhood identity, right? This is a theorem, and I think in this level of generality, we have to maybe Sanders is involved. Sanders, Shushofsky, Basikov, Wagner, I don't know.
I think this is
Yeah. So this is a statement, but using immutability. The relevant locally compact group is a kind of local Bohr compactification of the group generated by X. So I'll discuss later Bohr compactifications. Is the expression Bohr compactification okay, or should I of an abstract group? Or
Can you elaborate?
Yeah, I'll just say it, but I'll write it down later.
Sure.
Take an abstract group, discrete group, and this also makes sense for topological groups. But take a discrete group. You can look at homomorphisms of this group to compact Hausdorff groups. When I say compact, I mean Hausdorff with dense image. Look at all such things. And then there's a universal such object in some reasonable sense, which means that any such, let's call this a group compactification. This group compactification factors through this universal one. That's the Bohr compactification. It's the universal group compactification of a discrete group. For G, a non-discrete group, you require the map to be continuous. Okay? Anyway, you can try and develop this for maps to locally compact groups, and the relevant locally is a kind of local Bohr compactification, okay, which you have to explain what it means. Now, a remark is this also applies when, it's a quick remark, it also applies when X is a generic approximate subgroup, which means synthetic, and in that case, X is already commensurable with G, and assuming now G is amenable as a discrete group, but amenable as a discrete group just means that there's a left invariant, finitely valued, finitely additive probability measure on all subsets of G. That's it, which has got values between 0 and 1, for example. So in that case, you get a compact model, which actually is the Bohr compactification, and still with n equals 4. Now this result here, this is the case which I may restate this result. This we saw could be proved by various other people. We said Lupini. You mentioned Lupini and somebody else.
You're assuming G is
Amenable, yeah. Anyway, okay, I'll come. Just forget this parenthesis. Doesn't matter. Question: what can you say in general, namely without any amenability assumption? That's the question. There's a counterexample. So can you say something? Can you somehow prove something like theorem 0.4 in general? And there's a counterexample which, due to a paper of Khrushchevsky, Krupinski, and myself. By the way, this work I'm talking about is joint with Krzysztof Krupinski from Wrocław. Okay. A counterexample: you let F be the map from the free group on two generators, A, B to the integers, given by what I said, where sign is just 0, 1, right? Given if it's even or odd, if I'm not mistaken. And you have this now quasimorphism is just the map which is not a homomorphism. But quasi means that there could be some error set telling you how far it is from a homomorphism. And so we call it quasi, and the theme here is to get small error sets. Anyway, in this example, this is a counterexample. Now you look at graph of F as a subset of F2 cross the integers. F2 being the free group on two generators. And then so my group is now, the ambit group is F2 cross Z. And question?
Yeah, for the error term, you use what kind of metric?
For now, no metric. Just no metric. For now, no metric. So anyway, then you say X to be, X will be the graph of F is an approximate subgroup of F2 cross Z, and for which there's no locally compact one. And we proved this in some paper which appeared in Selector recently. Now, in a recent preprint called Beyond the Lascar Group, which is a very model theoretic paper, extremely logical paper. But I mean, logical, I don't mean just it makes logical sense, I mean, it's not logical, as we have to say sometimes. Is able to recover locally compact models in general, but with quasi-homomorphisms with small error sets, and small could mean something like compact, it could mean bounded in terms of certain, so metric. It could be, okay.
Well, Anand,
Yeah.
what does it mean, like, that there's a small number of places where it's not a homomorphism?
No, you take F, right, and you look at the collection of, you look at the set of, you look at F, a map from something to a group to a group, and you look at the collection of, say, F xy times F x to the minus 1, F y to the minus 1, is xy range over, and the other way around, and you, as xy range, and the unit of these sets is basically the error set. And I will talk about, in this question, I will discuss in certain ways that you can bound the error set. Anyway, he does this using in a recent paper, which is a little bit obscure for me, all right, in the work in logic, but with Kropinski, the idea is to obtain the same results, but via adapting topological dynamics to actions on locally compact spaces. So that's what we did. So topological dynamics is about the study, the abstract study of, say you start with a discrete group, you want to study the discrete group via its actions by homeomorphisms on compact spaces. So all these notions come from this amenability, minimal flow. I mean, all these things come from this setup. And we actually needed to generalize this to the actions of these kind of groups we're discussing, like the group generated by X, on the locally compact spaces. So that's what we did. But to simplify the exposition, and there was a lot of logic involved in that generalization, which at least I couldn't in a trivial way just rewrite everything in terms of ordinary mathematics. So to simplify the exposition, I'm going to focus on the case of understanding generic approximate subgroups, generic and approximate, where the existing topological machinery due to Ellis, Auslander, and Glasner and others suffices to, well, we have to prove something, right? But what we did, we had to do two things first: adapt to locally compact, and then prove some stuff. So now I want to do it where the adaptation locally compact is already there via compact. We just do compact, and that's what I want to discuss. So, okay, that's now. This could be a halfway part of the. It's not so great as good as half an hour. It's a kind of halfway house. So, any questions at this moment in time? No. Okay. So now I'm going to focus on the special case when we're studying generic approximates, so symmetric subsets of a group, with the property that finitely many translates of that set cover the group. Okay? Which is still an interesting context to me. So first of all, let me start by restating theorem 0.4, which is that. I'm restating what I have in parentheses, which is, I just put as a kind of, I shouldn't have written this anyway, I'm restating theorem 0.4 in the context of generic approximate subgroups. So I hope the definitions are okay of generic approximate. So here, the quantifiers change a little bit in terms of where the for all and their exists are. We were talking about quantifiers this morning, weren't we? At lunchtime. And so let G be a amenable discrete group. And again, this means that amenable, I say absolute discrete group, just means that there is let's say a left invariant, translation invariant, probability measure, finitely additive, not Borel, just finitely additive, on the Boolean algebra of all subsets of G. Okay? In fact, definition of meanable, another definition of meanable is whenever G is acting by homeomorphisms on a compact Hausdorff space, then there is a Borel probability measure on the space which is invariant under G. They're equivalent definition, they're equivalent characterizations. Then, given G amenable, there's a homomorphism F from G to a compact Hausdorff group C, such that for any generic approximate subgroup X of G, X to the 4, and it could be X to the squared or something, X to the 4, contains the pre-image of an open neighborhood identity U of C. This is the statement. So after passing to X to the 4, you get an explanation of genericity into, yeah, question?
Oh, is X symmetric?
Yeah,
I
because
think I forgot.
approximate includes, approximate just means symmetric. So so generic approximate is the same as symmetric and generic, or generic and symmetric. And the reason, if you don't put that in, if you don't put in symmetric, you'd have to include X to the minus 1 somewhere in
That's
that.
what I thought it would be.
That's it.
X,
It's a way of excluding having to put X to the minus 1s. Okay, this is the statement. This statement, I think, is something which has this paper, like you mentioned, Lapini and somebody else may put as a generalization of something that Bergelsen did with Benji Weiss and somebody else in the case of approximate subgroups of integers. I think. In fact, in this case, so here, the homomorphism doesn't depend on the choice of X, it works for all X. And the homomorphism is exactly the Bohr compactification of, I call it BG of G. The universal object among homomorphisms from G to compact groups with dense image. It's exactly the Bohr compactification. A quick slide. This theorem 5, right, is a positive theorem, uses amenability. And my next slide says that we can extend somewhat this positive result with homomorphisms of compact groups a little bit beyond the amenable context. So let me say what it is. Let me say what it is. And maybe somebody finds it interesting. I don't know. So I talk about beta G. I mean beta G, not BG, beta G. I mentioned beta, it should be like this. Beta G is the Stone-Check compactification of, maybe I put this downstairs. Yeah, beta G should be, it's a Stone-Check compactification of G. It's the profinite space of all ultrafilters on the Boolean algebra of all subsets of G. It's a classical object, I would say, in group theory. And if, okay.
I guess in theorem 0.5, this 4 cannot be improved, right?
I think that the issue is more subtle with what we were showing earlier, so I think that's right.
I think so, yeah. So one can define beta G as the space of all ultrafilters. So you should know what an ultrafilter is. Okay, I guess. We can define a multivariate operation, PQ. So I'll use P and Q to be ultrafilters. A multivariate operation, PQ on beta G, by P times Q, is the set of ultrafilters on G which contain the intersection of all subsets of G of the form X times Y for X in P, Y in Q. So X is a subset of G, Y a subset of Q. You say X times Y, the collection of products. This actually corresponds to a clopen subset of beta G, and you take the intersection of those clopen subsets. So it's a multivariate operation. And we look at, oh, I made a mistake. I made an error here. I forgot to say something. So So we look at the, oh Jesus, we look at the universal. We look at, sorry, excuse me. We look at F maps from B to G to arbitrary groups H, such that F of PQ, F of P times Q, this is a set, is the common value, is F of P times F of Q equals the common value of F of R for R in P times Q. So it's like a weak homomorphism, okay? So we look at maps like this, right? So this is not a, what? That's it. It's two groups, H. And let's say surjective maps with that property. And then there's a universal such thing, which I forgot to write down. This is an object which I'm going to call such map from B to G to a group H, surjective, which I call the weak Born compactification of G, WBG, of which the Born compactification is a quotient. So this WBG is actually a new invariant of the group G, which I don't think appeared anywhere else. It's not a topological group, it's not a compact group, it's a new invariant in some sense of that group. And the statement is, in this paper with Trotsky-Krupinski, suppose it so happens that the weak Born compactification of G coincides with Born compactification of G, which basically means that H is the structure of a compact group such that the map here is continuous. That's what it really means. Then there's an M depending only on G, such that for any generic approximate subgroup X of G, X to the M contains the preimage of an open neighborhood entity with respect to the canonical homomorphism from G to the Born compactification. So again, the compact model is Born compactification of G, and the M, measuring commensurability, depends only on G, not on X. So it's a slight improvement, and this goes beyond the amenable situation. I don't want to give examples, but most of the groups you'll find will satisfy this property, even if they're not amenable. Okay. So there are many counterexamples to the assumption WBG is BG. Actually, I'm saying now the opposite of what I said in the last sentence. There are many counterexamples. I said there's no. So sorry, I'm a little bit out now. There are many counterexamples. The assumption of theorem 0.6, as well as to extending the conclusion of theorem 0.6 to all G, such as when G is the universal cover of SL2R. This seems to be an interesting example. This is an example where these two. So for SL2R, it's a simple group, right? So its Born compactification is trivial because there's no map to anything. There's no homomorphism to anything, right? But it has a non-trivial weak Born compactification. Universal cover of SL2. As I promised, I've got about 20 minutes left. I'm going to go briefly through some classical constructions of abstract topological dynamics and just state what they yield in terms of generic approximate subgroups of arbitrary groups G. So we want to talk about arbitrary groups G. No assumption, nothing. Okay, no more assumption, just any group G, say something meaningful about generic approximate subgroups. So it's a bit technical. Apologies, and I'll say a theorem at the end, which also is technical, and I'm not sure, but I've got to say something with a theorem at some point. And when you get to the theorem, maybe it's not particularly comprehensible. But I'll go through this material. Okay, and I've got some time to do it. I may finish. It looks like I'll finish a bit early, but we have time for questions. So we start with an arbitrary G, and again, topological dynamics of the discrete group G is about studying the group G by its actions on compact spaces via homeomorphisms. That's what it's about. Okay. I'm going to start with beta G, which I already referred to. And beta G, the stone-check compactification of G, also known as the space of all ultrafilters on the Boolean algebra of all subsets of G. So all, I don't know to what extent this totally gets, I mean, I think this is a basic known object in mathematics, the stone-check compactification, but logic is there via ultrafilters in a sense, right? There is, logic belongs there. This is a G flow. So why is it a G? Now, a G flow just means, by G flow, I just simply mean the action of G by homeomorphisms on a compact space. That's a G flow. This is a G flow. Why? Because G acts on the collection of all subsets of itself by translation, right? By left translation, for example. So therefore, it acts on the set of ultrafilters on that collection of all subsets. And okay, and it acts by homeomorphisms. Now this is a G flow, and in fact, it's what's called the universal G ambit, the universal G flow with distinguished dense orbit. The dense orbit being G itself, because the points of G are like ultrafilters concentrating on one point, and that's a dense subset. This is the universal G ambit for G, a discrete group, is exactly the action on beta G. Now, beta G has a certain semigroup structure, which if somebody wants, I can give the definition of it. It's not going to be particularly enlightening, but it has a semigroup structure. It just means an associative map from beta G across beta G to beta G. Just semigroup is associative map, and which called star, which is continuous in the left coordinate. So I'm going to use PQ for these members of beta G because for emotional reasons, right? We use their types. So PQ, it means that you fix Q, then the map P to P star Q is continuous. That means left continuous. So you have this. So what I'm saying now is simply, is classical abstract topological dynamics in books of Ellis, Auslander. Which Auslander is it? There's a ring theory Auslander and there's the other. Do you know which Auslander it is? There's Louis and somebody got to know. Anyway, it's the other Auslander, not the ring theory Auslander. Louis? Maybe Louis. and now, an Ellis book is something, I think it's 70 something. Glasner, Auslander is 80s, I think. Glasner has a book called Proximal Flows, which is a Springer-Lexnode's book, which I think was his thesis in the middle 70s. And Glasner has a big effect on what, well, they all have a big effect on what. So this all comes from this classical material. Semigroup structures start on beta G. By the way, this use of topological dynamics, and there was a model theorist called Nowelski, who was a Polish model theorist. And about 15 years ago, he said that we can use this machinery to give new invariants in model theory for definable groups. And then from that point, I didn't believe him first, and in fact, I rejected a paper that he submitted to a journal of that ground that it was uninteresting. But I recommended it, as a referee, I think I recommended it, and then I changed my mind. Too late. So anyway, so this comes, our interest in this subject comes from actually, we should thank Nowelski, this Polish model theorist. Anyway, never mind. Semigroup structure star, beta G. I can write down what it is if you want later. Now, you take simply, forget the semigroup structure, you take a minimal subflow. That means simply you take beta G, a minimal G invariant closed subspace. That's a subflow. Subflow means closed invariant subspace under action of G. Minimal means minimal, smallest. And it's the same thing as a minimal left ideal, which means with respect to this star operation. So it's a subset which is an ideal, it's closed on the left by this multiplication operation. And this actually is the universal minimal G-flow. The universal minimal G-flow, which is another basic object attached to here, an abstract group. Now, on general grounds, this minimal, now there's lots of these people, there's lots of these minimal things, but the actions are all isomorphic. There's natural notion of an isomorphic, there's natural notion of an isomorphism, sorry, there's a natural notion of an isomorphism of G-flows, all right? Homomorphism respecting the action of G. So these are all isomorphic, these minimal flows. Now, on general grounds, you can find an idempotent in M. So we fix one of these minimal flows, M, curly M, and we find an idempotent, which means U star U equals U. Then U star M with the operation star is a subgroup. It's a group, actually, so it's therefore it's a subgroup of the semigroup. M is also a semigroup under star, but it's a group whose isomorphism type, and this group was typically studied as first an abstract group. As an abstract group, its isomorphism type is independent of the choices so far, and the choice of M and of U. Let me just see how much I've got to do. Okay, 3 more slides. Yeah. So far we have beta G, we have minimal flow, we have this semigroup structure, we have this idempotent, we have U star M. We've recovered a group, a certain group. However, I mean, M is closed. This UM is not closed in general. If U star M could equal M, actually, if there's a U star M could equal M, in which case it's actually, it's at least it's not a compact group, but it's a group. Well, okay, could equal M. But in general, it's not, as a set, it's not even a closed subset. So it doesn't have necessarily interest in topology. Okay, it's just a. Now, the most delicate construction of the whole business, I think it's due to Ellis. It appears in due to Ellis and is expanded on by Glasner, is a construction of the so-called tau topology or Tor topology on the group U star M, which will be a quasi-compact T1 separately continuous topology. Separately continuous means both left and right multiplication are continuous. But it's quasi-compact means compact, not necessarily Hausdorff. And T1 is what it means. It means you can separate, because if you have 2 points, you can find an open set containing this one and not this one. Isn't that right? T1. Right. So let me just say, let me just give one quick account of this Tor topology. For example, this U star M acts by star on the right on M, actually is the group of all automorphisms of the G flow M. Automorphisms means, in the category I said before, of homomorphisms respecting the group operation. So actually, this U star M has an interesting Galois theoretic nature. And there's actually a Galois theory that was introduced of these G flows using this. Anyway, U star M acts on the right as all automorphisms of the G flow M. Then we define for gamma a member of, so gamma here is going to be a member of then we say, I'm defining this new topology, this gamma is in the Tor closure of A if the graph of gamma, which is a subset of M cross N, is in the closure of the union of the graphs of the elements of A. The closure in what topology? Well, I mean, M is a sub, beta G is a topological space, right? Reduced topological, it's actually a profinite space. So M is a closed, M is a space. And so with that topology of beta G, induced by beta G, and M cross M, the product topology. So this is the topology here, is just the stone, what we call the profinite topology. The topology on M cross M is the product topology coming from the topology on M induced by that of beta G. Did I define the topology on beta G? No? Do I have to define the project on beta G? On the stone? Yeah. Space of all ultrafilters as a, well, maybe question time if somebody else wants to ask. So that's the, I'll give the definition of this tautology. But by all accounts, for me, it's the most mysterious aspect of the whole theory, which I would like to, yeah. Okay, good. Now we take the intersection of the Tor closures of all Tor open neighborhoods of the density in this group U star n. It's a normal closed subgroup of U star n. It's closed because it's the intersection of closures of things. And the quotient with the quotient topology turns out to be a compact Hausdorff group, which Glasner calls the generalized Born compactification of G. So Glasner was saying, again, you take SL2R, this Born compactification is trivial, but there should be something nice attached to it, you know? And in his book, he actually goes through in detail, I think, what's going on with SL2R, maybe as a discrete group, I forget. Anyway, this is a compact Hausdorff group, which I call it GBG. I'm calling it the generalized Born compactification. And it's another object which somehow you produce from this whole machinery. Right? And just in passing, let's mention that we have subjective homomorphisms, GBG, to this weak Born compactification I defined before, which itself goes on to the Born compactification, such that, now this is not a topological group, it's an abstract group, but such that the composition, this is a compact Hausdorff, the composition is continuous. And in model theory context, this was a kind of mysterious object that we had defined, and we didn't know where it came from, and we now see it as a image, as a quotient of a compact Hausdorff group. Okay, that was something for us which was a big deal. Let's now define a function. So I have this new compact Hausdorff group. Let's define a function f from the group G to this GBG, to this generalized Born compactification. It just takes f of g, as you take u star, u is this special idempotent, u star g cross u star, this is going to be in u star n, right? But just the image in the, after quotienting by that normal subgroup. This is the desired quasi-homomorphism from G to a compact group. This is the compact model. But the map is not a homomorphism, right? But this is the compact model. In the special case, we'll be on the generic approximation. So let me state maybe the theorem, then we'll stop. It's not, yeah, I'm a bit early, but we have questions on this. So that's it, okay? So we've got a map now from the group G to this compact Hausdorff group. And now the errors, left and right error sets. Left and right error sets, so I got it wrong already. Left one is fxy. These are subsets of, these things here are subsets of the target space, right? So it's f, the subsets of this GBG. Yeah, so fxy, fy minus 1, x minus 1, x, y, and g, that's the left error set. Other one is the right error set. And here is the theorem. Well, I'll just take the theorem. And there's a closed normal, there's a closed normal symmetric subset E of GBG, which is, I call it the error set, a canonical error set, which contains the left and right error sets of F. So E, right, so in the case of a homomorphism, E is just identity. E is, right? But the point is E will not be too large in the following sense, such that, so there's a closed normal subset E of GBG, containing left and right error sets of F, such that for any generic approximate subgroup X of G, for any one, the pre-image of C, x to the 30, there's a certain absolute number here, 30, x of it 30 times, contains the preimage of C. Just like contains the preimage of identity.
Let's see.
E, error. So there's an error set in two ways, right? There's two sets of error set. It's a typographical error and it's the error set. So,
Where is the number 30 coming from?
pardon?
Where is the number 30?
I don't know. I mean, let's think about 30. I mean, it's 30 years ago. What was I doing 30 years ago? I don't know. It comes from the. It's a good question, but it comes from some technical stuff playing with this star multiplication. Okay, and maybe it could be improved. This should be an E. Sorry, let's say so F. Yeah, sorry. I changed it to a C had two meanings or something. So let me restate it here. F minus 1. What is it? F minus 1E is in x to the 30. The only interesting thing is it's an actual number. I mean, I personally, I like numbers in the abstract, but I don't like any actual numbers. Just like people too. But I mean, so it's just a bit, but if you talk about number, you have to write the number down. So I've written it down. But I don't. Yeah, these are interesting questions about can you improve the number and things like that. But just having a number is enough for me. Having a particular number. Okay, that. This should also be There's a compact neighborhood. There's a compact neighborhood V identity in. Yeah, so by the way, let me say something. And if you have on general grounds, suppose F were a homomorphism. To GBG were a homomorphism. Right? And let's say Y in G and Y contains F minus 1 of the identity. Suppose you had, this is the analog form of the situation here. Suppose you had that, then on general grounds, even just logical grounds, and actually technical logical grounds, this implies that Y contains F minus 1U, the U open neighborhood of E in the group. If you're a homomorphism, on general grounds you get this. But here, right, we don't. So this should be an E. So plus, there's a compact neighborhood. There's a compact neighborhood. So it just means an open neighborhood identity. Maybe make it symmetric. In fact, V can be an open neighborhood. Doesn't matter. Such that F to the minus 1 of V is contained in x to the 14, and F to the minus 1, it should be VE, is contained in x to the 34. Okay, so why 34? I don't know, these are just particular numbers which come up in the proof. So the point is that this essentially explains, so F minus 1 VE is going to x34, this will actually imply that x34 is generic. So you get explanation of genericity in terms of quasi-homomorphisms to a compact group. And that's any group G. Okay, so that's it. Going to finish. In fact, it's almost exactly 5:15. Thank you.
Are there any comments or questions?
So the GBG is a compact Hausdorff group, right?
Yes.
So is it too much to hope for some kind of statement about the Haar measure of E?
I don't think you can get Haar measure being 0, for example. A good question, just control the Haar measure.
But even It doesn't even make sense to me.
Well, in some cases, I mean, if you go through there's an interesting case analysis for for the universal cover of SL2R, which in the model theory setting, where, so I don't know, so I'm just saying that in the model theory setting, where you think of SL2R universal cover is a definable group for this the model theory is in the two-sorted structure of the reals and integers, Z plus. And then the generalized bulk compactification is just Z hat. In Z hat, which means the universe is the what's it called? The profile at completion of Z. Z hat. That's the and the error set is finite in that context. It's a finite set, the error set. So it comes from the way that universal cover is built up by some two co-cycle from. So universal cover SL2R is built up from a certain two co-cycle from SL2R to Z, to SL2R to the center of the universal cover, which is it. So it comes. So there's a geometric meaning, and there's a nice geometric meaning of this in concrete situations.
Any other questions or comments?
Can I ask another one? So in the non-generic approximate subgroup case, in the more general statement, it's a locally compact group?
Yeah, so in general, right, so
yeah.
the fact, yes, yeah.
Yes, and sorry, so it's a locally compact group, you still have like an error set? Can you say that the hard measure of the error set is
Yes,
finite?
good, no, good, okay. So this was thanks for the question, I should have said this. So this, I'm going through the case of generic approximate, but the whole thing works also for approximate subgroups of arbitrary groups. In that case, this GBG is a locally compact group. The error set is compact. That's what we can say. The error set. So that's another issue about the error set. So in the locally compact settings, everything works exactly like this with the same numbers actually for X approximate subgroup of and G is replaced. Yeah, G. So general case with X in G. X is H, and this actually is what this is. Our G here becomes the H here, okay, and everything works. We have now a quasi-morphism from H to this locally compact group, and the same numbers, and the error set is compact. Okay. So,
Anything else? Let's thank the speaker again.
thank you very much.
There will be a dinner this evening, and you should contact Gay